Hello everyone, my name is Tanishq Sharma and in this presentation I will be discussing the master-slave architecture used in Liquid Galaxy and the reason behind choosing UDP as the communication protocol. This talk is part of the Liquid Galaxy streamings for GSoC 2026 pre-requirements. The focus of this presentation is not just on what technologies are used, but why these technologies are used and how they support Liquid Galaxy. So let us start by giving a quick introduction about what is Liquid Galaxy. Liquid Galaxy is an open source platform designed for immersive multi-screen visualization where multiple displays work together as a single display. It was originally created by Google engineer Jason Holt to run Google Earth across a cluster of PCs. But over time, it evolved far beyond the initial use case. Today, Liquid Galaxy functions as a general purpose visualization system capable of rendering complex geospatial data across multiple machines in real time. While it is often perceived that Liquid Galaxy is used only to run Google Earth on a cluster of machines. It is now also used widely for 2D and 3D virtual tours, geospatial data analysis, and many other interactive visual applications like even gaming, watching movies, etc. So now let us talk about what is the master-slave architecture. The master-slave architecture is a control and communication model in which one central node, called the master, has unidirectional authority over one or more subordinate nodes called slaves. And in this model is also called as the leader-follower architecture or the primary-secondary architecture. The master acts as the coordinator of the system, making decisions about task distribution, scheduling, and overall system state, while the slave nodes focus purely on executing the work assigned to them. The master keeps track of the status and health of all connected slaves, decides which slave should perform what action, and handles recovery when failures occur. Slaves typically do not communicate with each other directly and instead rely entirely on the master for instructions and coordination. This clear separation of responsibilities simplifies system behavior and ensures that all actions follow a single authoritative source of truth. Now, I would like to explain how the master-slave architecture works by taking an example from the Liquid Galaxy application. Let us say that we want to send a logo from our Liquid Galaxy app controller to the leftmost screen. In this case, it will be the slave with the ID 2. So, first we'll connect with the master machine from the Liquid Galaxy app. After that, we'll use this function. What this function is doing is that it is first defining a KML string in the KML content variable. After that, it is finding the ID of the leftmost screen using the calculate leftmost screen function. After that, it is executing the following command in on the master machine and then sending the KML file by redirecting the output from the KML content string into this file path. After that, the master handles the rendering of the logo on the leftmost screen. So now, why not the P2P architecture and what is the P2P architecture? The P2P architecture or the peer-to-peer architecture is a decentralized network model where every node has equal responsibility and can act as both as a client or as a server at the same time, that is, as a sender and a receiver. In a peer-to-peer system, nodes communicate directly with one another to share information and transmit data without relying on a central controller to manage the coordination. Why do we use the master-slave model and why it suits our requirement? In the Liquid Galaxy setup, multiple screens must behave as a single seamless panoramic display, which places very strict requirements on synchronization across all machines. When a user interacts with the system and moves the camera, even a small mismatch between screens can break the immersive experience. In a P2P or a peer-to-peer model, each screen would attempt to negotiate its own camera view with the neighboring screens, thus introducing coordination overhead and timing differences. And these minute timing differences are enough to cause visible tearing or misalignment in the screens. To avoid this, Liquid Galaxy relies on the master-slave model. Master-slave model is where, in this model, a single master computes the authoritative camera position and sends the command to all the slave nodes simultaneously. The master also handles processing master also handles processing user input and managing the global state, allowing the slave nodes to remain entirely dedicated to rendering their specific scene. By separating the control from rendering, the system minimizes latency and guarantees deterministic behavior across displays. Now, how does the master-slave architecture works in Liquid Galaxy? In Liquid Galaxy, synchronization is achieved by broadcasting only the camera view state from the master to all slave machines, rather than streaming imagery or rendered output. When the user moves the camera, the master sends small UDP packets known as the ViewSync messages containing parameters such as latitude, longitude, or there's the tilt, altitude, the heading, etc. These packets are sent at a high frequency by default over UDP and are intentionally lightweight to minimize the overhead. The master is configured to send these updates while slave machines are configured to receive them, ensuring that every camera movement is broadcasted immediately and simultaneously to all the slave nodes. Each slave applies a fixed yaw, pitch or roll offset locally, allowing it to render a view adjacent to the master's view to either left or right. This approach allows all machines to share a global state while keeping rendering fully distributed. Now, coming to the next slide, how does the master and slaves actually communicate with each other? And how does UDP plays a role in it? The communication between the master and slave machines in Liquid Galaxy is handled at the transport layer, which is responsible for end-to-end delivery of data between applications running on different machines. In the OSI model, this layer sits at a critical boundary because everything below it concerns how data is physically moved across the networks, while everything above it concerns how the application interprets and uses the data. For Liquid Galaxy, this distinction matters because the system already defines what needs to be communicated at the application level, namely camera and view state, and it does not need the transport layer to add additional semantics such as ordering or reliability beyond what the application itself requires. This makes the transport layer the natural decision point for controlling timing, latency, and delivery behavior. Protocols like TCP and UDP operate at this layer, but they impose very different constraints on how data flows between machines. In a multi-display system like Liquid Galaxy, where one master must continuously coordinate with several slaves, the transport layer directly influences whether updates arrive predictably and on time. The transport layer is not responsible for the correctness of content in this scenario, but for ensuring that the information reaches all rendering nodes quickly enough to preserve visual coherence across the panorama. Now, coming to the next slide, what is the requirement of the Liquid Galaxy setup? The Liquid Galaxy places very specific requirements on its communication model because all displays must behave as a single continuous visual surface. The system continuously produces camera updates as the user navigates, and these updates describe the complete current state of the view rather than incremental changes. This means that each update fully replaces the previous one and there is no dependency between successive messages. Because the camera is often moving smoothly and continuously, updates are generated at a high rate and the system expects them to reach all slave machines with minimal delay. In this context, the most important property of communication is freshness rather than completeness, or if an update arrives late, it no longer represents the current state and provides no benefit to the system. As a result, retransmitting outdated information does not improve correctness and can actively degrade responsiveness. The system is also designed to operate on a controlled local network, typically a wired LAN, where latency is low and packet loss is minimal. These constraints lead to a communication model where occasional loss is acceptable but delays are not. Now, moving to the next slide, why is the transmission control protocol not ideal for this use case? The TCP is designed such that it guarantees the ordered delivery of data and that the data will be transferred from the master to the slave or from one device to other. While this behavior is ideal for applications such as file transfers or web communication, it conflicts with the Liquid Galaxy's real-time synchronization needs. When a TCP segment is lost, the protocol must pause and retransmit that data before allowing the newer data to be delivered. Even if the newer data already represents a more accurate state, this introduces head of line blocking, where the entire stream is forced to wait for outdated information. This is also called the head of line blocking issue. In a multi-display environment, this can cause the slaves to fall behind the master's current camera position, resulting in visible lag rather than smooth motion. TCP's congestion control mechanisms further adjust sending rates dynamically, which can introduce unpredictable timing behavior that is harmful for synchronized rendering. Additionally, TCP is fundamentally point to point, meaning the master would need to maintain separate connections to each slave, increasing coordination overhead and coupling the performance of all displays together. These characteristics and features make TCP optimize for correctness of delivery rather than timeliness of state, which is what we require in Liquid Galaxy setup. But how does UDP fits these requirements? The user datagram protocol aligns closely with Liquid Galaxy's synchronization model as it allows the master to transmit the views immediately and simultaneously to all the slave machines. Each update is sent as an independent datagram, which means that every packet can be processed on its own without dependence on the previous messages. This matches Liquid Galaxy's state-based communication model where each update fully describes the current camera position. Because the user datagram protocol supports broadcast delivery on a local network, a single packet sent by the master can reach all slave machines nearly simultaneously, ensuring consistent timing across displays. The packets themselves are small, containing only the control information and minimal data so that the overhead is minimal and it can fit easily within the constraint of the network. Updates are sent frequently enough that if one packet is lost, the next one quickly corrects the view, implementing a last update wins behavior that keeps the system aligned in real time. Importantly, each slave processes packets independently, so slow or delayed reception on one node does not block others. By avoiding retransmissions, ordering constraints, and connection management, the user datagram protocol ensures predictable timing and low latency, which are essential for maintaining immersion in a synchronized panoramic display. In this context, UDP's lack of reliability is not a weakness, but a deliberate trade-off that enables smooth, responsive visualization across multiple machines. Now, I would like to show a demonstration that I've created using Python. To demonstrate the behavioral difference between TCP and UDP, I've created a small demonstration. So let me quickly explain the code. This is the TCP sender.py. This file is responsible for continuously sending sequential state updates over a TCP connection. We are using the socket.sock stream to create a TCP server and binding it using the host and port and starting to listen on it. It establishes a reliable connection with the receiver and sends incrementing value at a fixed interval, simulating the stream of a continuous camera state updates. As TCP guarantees ordered and reliable delivery, every value sent by the sender must eventually be received by the receiver in the same order, even if network delay or packet loss is introduced. And in this code, we are using this time.sleep method to introduce something like a network delay or a congestion. Now, let me quickly explain the receiver file. This file acts as the receiving end of the TCP connection. It continuously reads incoming data from the socket and prints each value down. As TCP preserves ordering, the receiver cannot skip values and it must wait for missing packets. Due to this property, which is also called as the head of line blocking, we'll see that the data comes in a particular order and as a particular group. So let me quickly show you the code, the the code works. CP sender.py, yes. And let me quickly run a new terminal. Let's move it into the editor area here. Now we can see Python TCP receiver tab, and here we go. As we can see that the data is coming in a particular group. So the values arrive in a particular order and as a part of a particular group. They might even come in batches and lag behind the sender. This happens because the TCP waits for the lost packets to be retransmitted before delivering the newer updates. Even though the sender has sent the fresh updates, the latest update, but still, due to the TCP's requirement of guaranteed delivery, the receiver cannot move forward until the older data arrives. This is a classic example of head of line blocking in TCP. The protocol enforces strict ordering, so the receiving buffer cannot advance until missing segments are recovered. In real-time systems like Liquid Galaxy, this causes the application to fall behind the actual state, creating latency rather than skipping intermediate updates. Now, let me quickly explain the code for the UDP sender and receiver. So this is the code for the UDP sender and receiver. This file does the same kind of sequential state updates as the TCP sender and it sends them over to the UDP receiver. Here we are using the socket.sock diagram to create a user datagram protocol socket with the and using it as the UDP server. And now let me quickly demonstrate how it works. Python TCP. No, this time it will be UDP sender.py. We'll go to the PowerShell. The UDP sender has started. We'll go to Python UDP and R tab, and here we go. So here we can see that the values arrive one by one. The some values might even go missing, but the receiver continues updating smoothly. This is because UDP is not waiting for lost packets. It is processing each value immediately, even if some updates never arrive and the data that is lost is lost. This demonstrates state-based communication. Each packet represents the current state and not a dependency on previous packets. Packet loss results in skipped states, not accumulated lag, which keeps the system aligned with real time. So this was all for the demonstration. Now coming back to the slides, to conclude, Liquid Galaxy prioritizes real-time freshness of state over strict delivery guarantees. A master-slave architecture enables precise and deterministic display synchronization by centralizing control and distributing rendering. UDP is chosen intentionally to minimize latency and avoid processing outdated data. These architectural and protocol choices are deliberate trade-offs to support the real-time synchronized display, multi-display experience, which is the core goal of Liquid Galaxy. So this is all for this presentation. Thank you.